All right, we're going to talk about the Doppler effect, okay? Let's talk a little bit about the Doppler effect, if I can get my full screen going here. Okay, so what is Doppler effect? I guess that's our first question here. So take a look right here, and this is in the context of speed, by the way. So since the speed of sound in a medium is constant, we can observe something called the Doppler effect, okay? And the Doppler effect is named after the Austrian physicist, Christian Doppler, who proposed it in 1842. Wow, that was a long time ago, right? Almost 200 years ago. 180 years ago. So if you ever heard if you ever heard a fire truck approaching and passing you, what does a siren sound like? You hear it in a distance, right? And then as it gets closer, what happens?
Get louder.
Gets louder, and then after it passes, it what? It starts to fade, right? Okay, so you got the idea. Okay, so the Doppler effect is in the change of frequencies of a wave, or what's called the periodic event, for an observer moving relative to the wave source, okay? And we'll watch that video later. For you at home, I'll put the link to the video in my Google Classroom for you to watch later. YouTube will not let me publish a video if I bring the video up while I'm recording this. So I'll put a separate video for you to watch shortly. Okay, so but let's move on here for right now. So let's look here right here. Stationary sound sources. Let's look right here. When a sound source is stationary, what's stationary mean? What's stationary mean, Terry? Do you know? Who knows what's stationary? It's staying still. Stationary means staying still. You're exactly right. What were you going to say there, Jaleel?
The bass.
Right. Okay, so when a sound source is stationary, the sound waves move outward. So here's the sound source right here. It's right here in the center, and it moves outwards, right? As it let's pretend this would be a tornado warning. You know, those don't go anywhere, right? They stand on the pole. They're not used only for tornado. Actually, they're used for thunderstorms and so on as well. So when a sound source is stationary, the sound waves move outward in all directions with an equal wavelength. And you see that right here. They're all at the same size waves. Got the idea? Okay. Gonna be a question here shortly. Okay, so now here's a moving sound source. And this would be an example. The other was an example of a tornado siren, right? Because we can identify with those here, can't we? Can we identify with those? Yeah. And so, but now here's an ambulance or a fire truck going down the road. And you see how that works, right? As the sound source moves right, it catches up with the wave that are produced and moves away. Okay, so it's moving away from its waves. So it moves away from the waves that move toward the left. So do you see the way the left and the right sides of the model look different? What's different? These are what? These are longer waves, right? These are shorter waves. Shorter waves, the closer they are to the moving model. Okay. Okay, so let's move on here. So again, the moving sound sources. Talk a little bit more about that. So since the speed of the sound waves that are produced is constant, and the wavelength is changed back both in front as well as in the back of the moving source. You see that they get larger as they go away, right? Look at here, they get larger. Okay, as well as in back of the moving source, there's also a change in the frequency of the wave. So what does the frequency mean? Well, let's find out here. So how would this affect the pitch of the sounds that are heard? Well, let's find out. Okay, so here we go. You ready? Here's a question for you. You got this, Jaleel? The Doppler effect is a change in frequency and wavelength of a wave when the wave source is in motion compared to the observer. Is that a true statement or a false statement? Mark your answer. The Doppler effect, that's a change. Now, this is the moving. When you think of the Doppler effect, think of the moving fire truck. Did the wavelengths change? Did they change? True or false? This says they changed, so either mark true if that's true, mark false if it's wrong. Okay, I'm going to go to the next one here. Okay, so let's look at this question. Jaleel, I need your attention here. When a train blowing its horn is moving towards you, you hear what? Do you hear a higher pitched sound, the same pitch that's produced, or a lower pitched sound? Mark your answer, A, B, or C. It's okay to be wrong, it's not the end of the world. A, B, or C. A higher pitched sound, the same pitch that's produced, or a lower pitched sound as it's moving toward you. Okay, when a train blowing its horn is moving away from you, you hear what? A higher pitched sound, the same pitch, or a lower pitched sound? It's okay to be wrong. Jaleel?
Yeah.
I need you with me here. Okay. Here's another one. Look right here. When a train blowing its horn is not moving compared to you, you hear what? The higher pitched sound, the sound pitch that's produced, or a lower pitched sound? Got an answer for that, for 54 there, Jaleel?
53, you mean?
No, this is 54. I'm on 54 now. Yes, sir, buddy. Okay, 55. There is no 55. Okay, so let's move on here. So what happens when the observer is moving? So how we're moving, okay? So the Doppler effect works for both a moving sound source as well as a moving observer, okay? That'd be like if you're in a truck and you're going away from the sound. Okay, we still observe an increase in frequency even if the observer is moving rather than the sound source. So, and again, I'll put this video on you for you at home. We're going to move on for right now. Let's look right here. Actually, we're going to stop that right here. We're going to stop this lesson for the day. And we'll come back to this the next lesson. Okay?